Hi, I'm Amanda, and I'm a RealityKit engineer.
And I'm Max. I'm a SwiftUI engineer.
Today, we'll share some great enhancements to both SwiftUI and RealityKit that help them work even better together. Check out this adorable scene. We've got a charming SwiftUI robot hovering in midair and a grounded RealityKit robot, both yearning for connection. When they get close, sparks fly. But how can they get close enough to truly interact? Max and I will share how to combine the worlds of traditional UI and interactive 3D content. First, I'll share some enhancements to Model 3D. Then, I'll demonstrate how to transition from using Model 3D to using RealityView, and talk about when to choose one versus the other. I'll tell you about the new Object Manipulation API. RealityKit gets new component types, integrating more aspects of SwiftUI. Information can now flow both ways between SwiftUI and RealityKit. We'll explain. Coordinates-based conversion is easier than ever. Drive RealityKit component changes with SwiftUI animations. Let's wire it up. Display 3D models in your apps with just one line of code using Model 3D. In visionOS 26, 2 enhancements let you do even more with Model 3D. Playing animations, and loading from a configuration catalog. Since Model 3D is a SwiftUI view, it participates in the SwiftUI layout system. I'll use that layout system to make a little sign that displays the robot's name. Now the sign says that this robot's name is Sparky. Sparky also has some sweet dance moves. The artist bundled this animation with the robot model asset. New in visionOS 26 is the Model 3D asset type. Load and control your animations on your 3D content by constructing a Model 3D using a Model 3D asset. The model loads the animations from the asset and lets you choose which one to play. Model is an overloaded term, especially in this session, as we're converging a UI framework and a 3D game framework. In UI frameworks, a model refers to the data structure that represents the information your app uses. The model holds the data and business logic, allowing the view to display this information. In 3D frameworks like RealityKit, a model refers to the 3D object that can be placed in a scene. You access it via the model component, which consists of a mesh resource that defines its shape and materials that determine its appearance. Sometimes that happens. 2 worlds collide, bringing their terminologies with them. And sometimes there's overlap. Now, back to Sparky and its animation. I'm placing the Model 3D above a picker, a play button, and a time scrubber. In my robot view, I'm displaying the animated robot itself, and under that, I'm placing a picker to choose which animation to play, plus the animation playback controls. First, I'm initializing a Model 3D asset with the scene name to load from my bundle. Then, once the asset is present, I pass it to the Model 3D initializer. Underneath that, in the VStack, I'm presenting a customized picker that lists the animations that are available in this model asset. When an item is chosen from the list, the picker sets the asset's selected animation to the new value. Then, the Model 3D asset creates an animation playback controller to control playback of that chosen animation. The asset bends an animation playback controller. Use this object to pause, resume, and seek in the animation. I'm passing that animation controller into my Robot Animation Controls view, which we'll also look at shortly. In visionOS 26, the existing RealityKit class Animation Playback Controller is now observable. In my SwiftUI view, I observe the time property to display the animation's progress. I have a bindable property called Controller, which means I'm using the Animation Playback Controller as my view's data model. When the controller's isPlaying value changes, SwiftUI will reevaluate my Robot Animation Controls view. I've got a slider that shows the current time in the animation relative to the total duration of the animation. You can drag this slider, and it will scrub through the animation. Here's Sparky doing its celebration animation. I can fast forward and rewind using the slider. Go, Sparky. It's your birthday. With its dance moves down, Sparky wants to dress up before it heads to the greenhouse to meet the other robot there. I can help it do that with enhancements to RealityKit's ConfigurationCatalog type. This type stores alternative representations of an entity, such as different mesh geometries, component values, or material properties. In visionOS 26, you can initialize a model 3D with a configuration catalog and switch between its various representations. To allow Sparky to try on different outfits, my artist bundled a reality file with several different body types. I load this file as a configuration catalog from my app's main bundle. Then, I create my model 3D with the configuration. This popover presents the configuration options. Choosing from the popover changes Sparky's look. Dance moves, check. Outfit, check. Sparky is ready to meet its new friend in the RealityView greenhouse. Sparks are gonna fly. To make those sparks fly, I'll use a particle emitter. But that's not something I can do at runtime with the Model 3D type. Particle emitter is a component that I add to a RealityKit entity. More on that in a moment. Importantly, Model 3D doesn't support adding components. So, to add a particle emitter, I'll switch to RealityView. I'll share how to smoothly replace my Model 3D with a RealityView without changing the layout. First, I switch the view from Model 3D to RealityView. I load the botanist model from the app bundle inside the make closure of the RealityView, creating an entity. I add that entity to the contents of the RealityView so Sparky appears on screen. But now the name sign is pushed too far over to the side. That wasn't happening before when we were using a Model 3D. It's happening now because, by default, RealityView takes up all the available space that the SwiftUI layout system gives it. By contrast, the Model 3D sizes itself based on the intrinsic size of the underlying model file. I can fix this. I apply the new RealityView layout behavior modifier with fixed size to make the RealityView tightly wrap the model's initial bounds. Much better. RealityView will use the visual bounds of the entities in its contents to figure out its size. This sizing is only evaluated once, right after your make closure is run. The other options for RealityView layout behavior are flexible and centered. In all three of these reality views, I have the bottom of the Sparky model sitting on the origin of the scene, and I've marked that origin with a gizmo, the little multicolored cross showing the axes and origin. On the left, with the flexible option, the reality view acts as if it doesn't have the modifier applied. The origin remains in the center of the view. The centered option moves the origin of the reality view so that the contents are centered in the view. Fixed size makes the reality view tightly wrap the contents bounds and makes your reality view behave just like Model 3D. None of these options reposition or scale your entities with respect to the reality view content. They just reposition the reality view's own origin point. I've sorted out Sparky's sizing in the reality view. Next, I'll get Sparky animating again. I'll move from Model 3D's new animation API to a RealityKit animation API directly on the entity. For more detail on the many ways of working with animation in RealityKit, check out the session Compose Interactive 3D Content in Reality Composer Pro. I switched from Model 3D to RealityView so I could give Sparky a particle emitter component because sparks need to fly when these two robots get close to each other. Particle emitters let you make effects that involve hundreds of tiny particles animating at once, like fireworks, rain, and twinkles. RealityKit provides preset values for these, and you can adjust those presets to get the effect you're after. You can use Reality Composer Pro to design them, and you can configure them in code. You add the particle emitter to an entity as a component. Components are a central part of RealityKit, which is based on the Entity Component System paradigm. Each object in your scene is an entity, and you add components to it to tell it what traits and behaviors it has. A component is the type that holds data about an entity. A system processes entities that have specific components, performing logic involving that data. There are built-in systems for things like animating particles, for handling physics, for rendering, and many more. You can write your own custom system in RealityKit to do custom logic for your game or app. Watch Dive into RealityKit 2 for a more in-depth look at the entity component system in RealityKit. I'll add a particle emitter to each side of Sparky's head. First, I make 2 invisible entities that serve as containers for the sparks effect. I design my sparks emitter to point to the right. I'll add it directly to my invisible entity on Sparky's right side. On the other side, I rotate the entity 180 degrees about the y-axis so it's pointing leftward. Putting it all together in the RealityView, here's Sparky with its animation, its name sign in the right position, and sparks flying. RealityKit is great for detailed creation like this. If you're making a game or play-oriented experience, or need fine-grained control over the behavior of your 3D content, choose RealityView. On the other hand, use Model 3D to display a self-contained 3D asset on its own. Think of it like SwiftUI's image view, but for 3D assets. Model 3D's new animation and configuration catalogs let you do more with Model 3D. And if your design evolves and you need direct access to the entities, components, and systems, transition smoothly from Model 3D to RealityView using RealityView layout behavior. Next, I'll share details about the new Object Manipulation API in visionOS 26, which lets people pick up the virtual objects in your app. Object manipulation works from both SwiftUI and RealityKit. With object manipulation, you move the object with a single hand, rotate it with one or both hands, and scale it by pinching and dragging with both hands. You can even pass the object from one hand to the other. There are 2 ways to enable this, depending on whether the object is a RealityKit entity or a SwiftUI view. In SwiftUI, add the new Manipulable modifier. To disallow scaling, but keep the ability to move and rotate the robot with either hand, I specify what operations are supported. To make the robot feel super heavy, I specify that it has high inertia. The Manipulable modifier works when Sparky is displayed in a Model 3D view. It applies to the whole Model 3D, or to any view that it's attached to. When Sparky's in a reality view, I want to enable manipulation on just the robot entity itself, not the whole reality view. In visionOS 26, manipulation component is a new type that you can set on an entity to enable object manipulation. The static function ConfigureEntity adds the manipulation component to your entity. It also adds a collision component so that the interaction system knows when you've tapped on this entity. It adds an input target component, which tells the system that this entity responds to gestures. And finally, it adds a hover effect component, which applies a visual effect when a person looks at or hovers their mouse over it. This is the only line you need to enable manipulation of an entity in your scene. To customize the experience further, there are several parameters you can pass. Here, I'm specifying a purple spotlight effect. I'm allowing all types of input, direct touch, and indirect gaze and pinch. And I'm supplying collision shapes that define the outer dimensions of the robot. To respond when a person interacts with an object in your app, the object manipulation system raises events at key moments, such as when the interaction starts and stops, gets updated as the entity is moved, rotated, and scaled, when it is released, and when it is handed off from one hand to another. Subscribe to these events to update your state. By default, standard sounds play when the interaction begins, a handoff occurs, or the object is released. To apply custom sounds, I first set the audio configuration to none. That disables the standard sounds. Then I subscribe to the manipulation event did handoff, which is delivered when a person passes the robot from one hand to the other. In that closure, I play my own audio resource. Well, Max, Sparky's journey has been exciting. Animating in Model 3D, finding its new home in a RealityView, showing its personality with sparks, and letting people reach out and interact with it. It's come a long way on its path toward the RealityKit greenhouse.
It sure has. But for Sparky to truly connect with the robot waiting there, the objects in their virtual space need new capabilities. They need to respond to gestures, present information about themselves, and trigger actions in a way that feels native to SwiftUI. Sparky's journey towards the RealityKit greenhouse is all about building connection. Deep connection requires rich interactions. That's exactly what the new SwiftUI RealityKit components are designed to enable. The new components in visionOS 26 bring powerful, familiar SwiftUI capabilities directly to RealityKit entities. RealityKit introduces three key components. First, the view attachment component allows you to add SwiftUI views directly to your entities. Next, the gesture component makes your entities responsive to touch and gestures. And finally, the presentation component, which presents SwiftUI views like popovers from within your RealityKit scene. visionOS 1 let you declare attachments upfront as part of the RealityView initializer. After evaluating your attachment view builder, the system called your update closure with the results as entities. You could add these entities to your scene and position them in 3D space. In visionOS 26, this is simplified. Now you create attachments using a RealityKit component from anywhere in your app. Create your view attachment component by giving it any SwiftUI view. Then, add it to an entities components collection. And just like that, I moved our name sign from SwiftUI to RealityKit. Let's explore gestures next. You can already attach gestures to your RealityView using targeted to entity gesture modifiers. New in visionOS 26 is gesture component. Just like view attachment component, you add gesture component to your entities directly, passing regular SwiftUI gestures to it. The gesture values are by default reported in the entity's coordinate space. Super handy. I use gesture component with a tap gesture to toggle the name sign on and off. Check it out. The robot's name is Bolts. Pro tip: on any entity that's the target of a gesture, also add both input target component and collision component. This advice applies to both gesture component and the target gestures API. Gesture component and view attachment component let me create a name sign for Bolts. But Bolts is getting ready for a special visitor, Sparky. Bolts wants to look its absolute best for their meeting in the greenhouse. Time for another outfit change. I'll replace Bolts' name sign with UI to pick what Bolts will wear. Truly a momentous decision. To emphasize that, I'll show this UI in a popover using presentation component directly from RealityKit. First, I'll replace view attachment component with presentation component. The component takes a Boolean binding to control when the popover is presented and to notify you when someone dismisses the popover. The configuration parameter is the type of presentation to be shown. I'm specifying popover. Inside the popover, I'll present a view with ConfigurationCatalog options to dress up Bolts. Now I can help Bolts pick its best color for when Sparky comes to visit.
Hey Max, do you think Bolts is more of a summer or an autumn?
That's a fashion joke.
Bolts is dressed to impress. But first, it has to go to work. Bolts waters plants in the greenhouse. I'll make a mini-map, like on a heads-up display in a game, to track Bolts' position in the greenhouse. For that, I need to observe the robot's transform component. In visionOS 26, entities are now observable. They can notify other code when their properties change. To be notified, just read an entity's observable property. From the observable property, you can watch for changes to the entity's position, scale, and rotation, its children collection, and even its components, including your own custom components. Observe these properties directly using a with observation tracking block. Or lean on SwiftUI's built-in observation tracking. I'll use SwiftUI to implement my minimap. To learn more about observation, watch Discover Observation in SwiftUI. In this view, I display my entity's position on a minimap. I'm accessing this observable value on my entity. This tells SwiftUI that my view depends on this value. As Bolts moves about the greenhouse, watering the plants, its position will change. Each time it does, SwiftUI will call my view's body again, moving its counterpart symbol in the minimap. For a deeper explanation of SwiftUI's data flow, check out the session Data Essentials in SwiftUI.
Our robot friends are really coming together.
That's the dream.
I like your description of the difference between model and model earlier.
And sometimes you need to pass data from your data model to your 3D object model, and vice versa.
In visionOS 26, observable entities give us a new tool to do that.
Since the beginning, you could pass information from SwiftUI to RealityKit in the update closure of RealityView. Now, with entity's observable property, you can send information the other way. RealityKit entities can act like model objects to drive updates to your SwiftUI views. So, information can flow both ways now, from SwiftUI to RealityKit and from RealityKit to SwiftUI. But does this create the potential for an infinite loop? Yes. Let's look at how to avoid creating infinite loops between SwiftUI and RealityKit. When you read an observable property inside the body of a view, you create a dependency. Your view depends on that property. When the property's value changes, SwiftUI will update the view and rerun its body. RealityView has some special behavior. Think of its update closure as an extension of the containing view's body. SwiftUI will call the closure whenever any of that view's state changes, not only when state that is explicitly observed in that closure changes. Here, in my RealityView's update closure, I'm changing that position. This will write to the position value, which will cause SwiftUI to update the view and rerun its body, causing an infinite loop. To avoid creating an infinite loop, don't modify your observed state within your update closure. You are free to modify entities that you're not observing. That won't create an infinite loop, because changes to them won't trigger SwiftUI to reevaluate the view body. If you do need to modify an observed property, check the existing value of that property and avoid writing that same value back. This breaks the cycle and avoids an infinite loop. Note that the RealityView's make closure is special. When you access an observable property in the make closure, that doesn't create a dependency. It's not included in the containing view's observation scope. Also, the make closure is not rerun on changes. It only runs when the containing view first appears. You can also update the properties on an observed entity from within your own custom system. A system's update function is not inside the scope of the SwiftUI view body evaluation. So this is a good place to change my observed entity's values. The closures of gestures are also not inside the scope of the SwiftUI view body evaluation. They are called in response to user input. You can modify your observed entity's value here, too. To recap, it's cool to modify your observed entities in some places and not in others. If you do find that you have an infinite loop in your app, here's a tip for fixing it. Split up your larger views into smaller, self-contained views, each one having only their own necessary state. That way, a change in some unrelated entity won't cause your small view to be reevaluated. This is also great for performance. You know, Max, you might find that you don't need to use your update closure at all anymore. Since your entity can now be your view's state, you can modify it in the normal places that you're used to modifying state, and forgo the update closure altogether.
Yeah, I feel like avoiding infinite loops is something I have to learn over and over again. But if I don't use an update closure, I'm less likely to run into one.
I think it's time to bring Bolts and Sparky together.
Bolts is finally done with work. Time for its date with Sparky. As I pick up Sparky to bring it over, and the two robots get closer together, I want to make sparks fly as a function of the decreasing distance between them. I'll use our new Unified Coordinate Conversion API to enable this. Sparky is in the Model 3D SwiftUI view now, and Bolts is an entity in the RealityKit greenhouse. I need to get the absolute distance between these two robots, even though they're in different coordinate spaces. To solve this, the spatial framework now defines a coordinate space 3D protocol that represents an abstract coordinate space. You can easily convert values between any two types that conform to coordinate space 3D, even from different frameworks. RealityKit's entity and scene types conform to coordinate space 3D. On the SwiftUI side, Geometry Proxy 3D has a new coordinate space 3D function that gives you its coordinate space. Additionally, several gesture types can provide their values relative to any given coordinate space 3D. Coordinate space 3D protocol works by first converting a value in Sparky's coordinate space to a coordinate space shared by both RealityKit and SwiftUI. After that, it converts from the shared space into Bolt's coordinate space, while taking low-level details like points to meter conversion and axis direction into account. In Sparky's Model 3D view, whenever the view geometry changes, the system calls my onGeometryChange3D function. It passes in a Geometry Proxy 3D, which I use to get its coordinate space. Then, I can convert my view's position to a point in the entity space, so I know how far apart my two robots are from each other. Now, as Amanda brings Bolts and Sparky together, the sparks increase. As she pulls them apart, the sparks decrease. Next, I'll teach these robots to move together and to coordinate their actions. I'll use SwiftUI-driven animation for RealityKit components. SwiftUI already comes with great animation APIs to implicitly animate changes to your view properties. Here, I animate the Model 3D view that Spark is in. I send it over to the left when I toggle, and then it bounces back to the original position when I toggle again. I'm adding an animation to my isOffset binding, and I'm specifying that I want an extra bouncy animation for it. In visionOS 26, you can now use SwiftUI animation to implicitly animate changes to RealityKit components. All you need to do is set a supported component on your entity within a RealityKit animation block, and the framework will take care of the rest. There are two ways to associate an animation with a state change. From within a RealityView, you can use content.animate to set new values for your components inside the animate block. RealityKit will use the animation associated with the SwiftUI transaction that triggered the update closure, which in this case is an extra bouncy animation. The other way is to call new entity.animate function, passing a SwiftUI animation and a closure that sets new values for your components. Here, whenever the isOffset property changes, I send Sparky left or right using the entity's position. Setting the position inside the animate block will begin an implicit animation of the transform component, causing the entity to move smoothly to the new position. The power of implicit animation really shines when I combine it with the object manipulation API that Amanda introduced. I can use a SwiftUI animation to implement a custom release behavior for bolts. I'm first going to disable the default release behavior for object manipulation by setting it to stay. Then, I will subscribe to the will release event for the manipulation interaction. And when the object is about to be released, I will snap Sparky back by setting its transform to identity, which resets the scale, translation, and rotation of the entity. Since I'm modifying Sparky's transform inside the animate block, Sparky will bounce back to its default position. Now, Sparky's animation back to its original position is much more fun. All these built-in RealityKit components support implicit animations, including the transform, the audio components, and the model and light components, which have color properties. Sparky and Bolts had quite a journey.
It's so great to see the power of SwiftUI and RealityKit working together.
With this connection, you're also empowered to develop truly exceptional spatial apps, fostering a real connection between the virtual and the physical.
Imagine the possibilities as you seamlessly integrate SwiftUI components into your RealityKit scenes. and as entities dynamically drive changes to your SwiftUI state.
Just like Sparky and Bolts, we hope you're inspired to connect SwiftUI and RealityKit in ways we haven't even imagined yet.
Let's build the future together.